Welcome back, everyone. Our next talk is Quantum Machine Learning with PennyLane with Thomas Bromley. Before I tell you some key facts about this talk, I would like to encourage you to keep the discussion going on Discord and to ask all of your questions during the talk so we can answer them later. So, without further ado, first off, PennyLane is a Python-based library for quantum differentiable programming. It combines quantum circuits with existing machine learning frameworks to create unique hybrid models. This talk provides an introduction to quantum machine learning and PennyLane, showing you how to set up and train quantum models for machine learning problems. Tom studied physics in the UK, and after graduating, he moved straight to Xanadu to join the quantum machine learning team. As well as research, Tom's role includes software development and engaging with clients on potential quantum solutions. Enjoy the talk.
Hi, everybody. This is Thomas Bromley. I am a quantum software engineer and researcher working at Xanadu. I'm very excited to tell you about quantum machine learning and how to use PennyLane. So just a little bit of an intro to Xanadu if you haven't heard of us. These are all our faces. Founded about 4 years ago now, and we've certainly grown over that time. And we're based in downtown Toronto. Really, our mission is to build quantum computers that are useful and accessible to people everywhere. So we have a bit of a couple of focuses. So one focus is, of course, on the hardware side. So we're building out a photonic quantum computer. We also have a big focus on the software side. So that's things like PennyLane. We also have another package called Strawberry Fields, which is aimed at simulating our device. But today I'm going to be talking about PennyLane. So just a little step back a bit, just to talk about quantum computing. I'm sure many of you might have attended the earlier talks on quantum computing, but if you're just coming in fresh, really the way to think about it is it's a very unique paradigm. You can't really compare it to classical computing, just an entirely different model, say. So we have quantum systems now. We describe them in terms of qubits typically. So these are like a quantum version of a classical bit. And how we manipulate them, well, we apply quantum gates to these qubits, and how we then arrange these gates forms a quantum circuit or a quantum algorithm. And that can do certain tasks, sort of equivalent algorithms to what you would get on a classical computer. So really the power comes from these underlying quantum effects that you might have heard of, things like entanglement, things like superposition. And how do we actually think about designing these quantum circuits? So yeah, again, you might have seen this before. So when we design a quantum circuit, we typically have qubits along these wires here. So each wire here is a qubit, and we then have gates here, these boxes. So a gate can act on just one qubit. It can be a transformation on one of the qubits, but it can also couple qubits together. So this gate here, it could create entanglement between the qubits. Then at the end, we typically measure the qubits and we find out what state they're in. So that's how we, at a very high level, think about designing a quantum circuit. Of course, there's a lot of art into where you place these gates and which gates you choose. But now let's think a little bit about quantum computing in terms of machine learning. So suppose we have some circuit, we've set up a circuit, and we've got a gate here. It can depend on a free parameter, some theta, for example. So if you've heard of these, you could be a rotation gate, for example, if you've heard of them. And so we can have an even larger circuit, but let's consider this particular gate with the theta. Now we can look at the expectation value, the output of our circuit. So this function f, it depends, of course, on theta, but actually it depends in a well-behaved sort of way. And you can think of quantum circuits as things that are differentiable. So that leads to this very nice philosophy that, okay, we have some, maybe we can put in some data x, and we have some controllable parameters theta, and we have a function that can be differentiated with respect to theta. Let's differentiate it. Let's train this function f and use it for things like optimization and use it for things like machine learning. So really the idea is we say, okay, let's get this quantum computer or a quantum circuit, vary the parameters. It's just like it's kind of like a neural network, and we train a bit like that. So, okay, a bit more on how we train. So this fleshes it out a bit more. So what we typically do is we have a fixed layout for our quantum circuit. So we have these are rotation gates here. These ones are fixed, but we have another sort of layer of controllable rotations. So here we have these theta parameters, these theta 1, theta 2, theta 3, and theta 4. And they then go on to influence the expectation value, the output of our quantum circuit. And here is just a visualization of, it's essentially just plotting a function that depends on both of these thetas. So really that's the idea of quantum circuits. They're differentiable functions. They can be, here it looks fairly simple, but they can actually be quite complicated functions as well. And that's kind of where this power of quantum is coming in. So let's be a bit more specific. How could this be interesting for machine learning, for example? So one of the things that we've looked at is quantum transfer learning. And really, the idea is that, so in transfer learning, you train a model on a specific problem or data set. Then what you do is, say this model is a neural network, you chop off the last few layers, and then you swap in like a follow-up. Say this could be another few layers of the neural network. You add that in at the end. So you've got a pre-trained network and then an untrained few layers. And what you do is you then you train the untrained layers on a new task. And the idea is that the trained layers, this pre-trained model at the start, this can be used to sort of transfer learning from a similar task to another task. So yeah, the example here is that we have, you can train a ResNet on images, and then you can specify, okay, let's restrict the task to maybe classification of bees versus ants. But the cool thing is so this is standard transfer learning, but instead, what if we say, okay, this final set of layers, let's swap it out for a trainable quantum circuit. So now we're creating a hybrid model. We're sticking on an established neural network model, this ResNet, but we're adding on a trainable quantum circuit. Can we train it? How well does it do? So this is something you can check out more details online on our website. But yeah, it turns out you can train it, and it does manage to classify bees versus ants. And yeah, to a similar sort of competitive accuracy of ResNet, for example. So this then leads to the question of how do we do this? How do we train this model? So this is what PennyLane is for. So PennyLane is an open source Python framework for near-term differentiable quantum programming. So that's kind of our tagline of how we're describing it, but really we think of it as it's a machine learning library applied to quantum, so a quantum machine learning library. Now, let's show a bit of code. So we have actually a teaser demo here just to show you a little bit of PennyLane code. It's kind of the Hello Quantum World, so the quantum version of Hello World. And for us, you can think of this as, it's actually just a rotation. So one way to describe a qubit is that you have this sphere. And I guess the details don't matter too much, but a state on the sphere is just an arrow pointing to a particular point on the surface of the sphere. What we want to do is we want to train a circuit to rotate our arrow from the North Pole to the South Pole. We have a pretty simple circuit to look at. So here we have a certain type of rotation and then a certain orthogonal type of rotation. This could all be, like, we know the optimal choices of these parameters, but it's a nice, again, it's a hello world. So it's a nice way to just try out and see how PennyLane can learn these optimal parameters, theta 1 and theta 2, to get us to do this rotation from North Pole to South Pole. So how does it look like in code? Well, we start off, there's some usual inputs that we might expect to do. You can see we're actually importing PyTorch. So PennyLane interfaces with PyTorch and other libraries like TensorFlow. Here we're showing the example of interfacing with PyTorch. Then the first PennyLane step really is to choose your device. So we load our QPU is So this QML device, it could be loading a simulator, or it could load hardware. In this example, we're loading hardware. So this Forest QPU is a quantum processor from Rigetti. So we're loading this up. And now we define something called a QNode. So this QNode is really our way of thinking about this quantum function. So a QNode really is you have some classical input data, some non-quantum input data. Then you do all your gates, you do your measurements, and then you have some non-quantum data coming out. So really you can think of it as just one node in a larger computational graph. So this is why we call it a QNode, but another way to kind of think about it is just a quantum circuit. So what we do is we define our circuit here. We have this functional approach. So we define our circuit as a function. We apply some rotation gates, and we define what we're returning. So this is a measurement, this is an expectation value in the computational basis. And we then add this decorator, qml.qnode. We pair up our circuit with our device, and we say, okay, we want the PyTorch interface. Then the rest really is just classical optimization. So we say, okay, let's have a cost function here. It depends on our two parameters, the parameters that we're training. We evaluate our circuit, and then we define the cost function to be, so this is, we want the expectation value, the output of the circuit, we want it to get to -1, which corresponds to going to the south pole here. So once we've defined our cost function, yeah, it really is just standard, really PyTorch from here. So we load our variables, these phi1s and phi2s. We pick an optimizer, so we're using the Atom optimizer. You're free to choose other ones. And then we run the optimization loop. And yeah, here on the side, it's really just a visualization where we've trained, but what we've done is we've flipped the objective every number of iterations. So we're going, okay, get us to the South Pole. Then a bit later, we're saying, you've done a good job of that, get us back to this North Pole. So that's just a nice teaser demo to show you a bit of code in PennyLane. Now I'm going to talk a little bit about what are PennyLane's features. What can you do with it more concretely? So the foundation really is this built-in support for quantum gradients. So PennyLane is built around the ability to have this quantum circuit, some trainable parameters, and to naturally be able to access the derivative of the circuit with respect to the parameters. So it's not so much a kind of hacking it in approach, it's built around different quantum differentiable programming. So you can see here we have our QNode decorator that converts our circuit into a PennyLane QNode. And the key here is that we're specifying how we do our differentiation, so our differentiation method. So here we have parameter shift. There are some other options, so I can talk you through them here. So the parameter shift rule, this is one way to evaluate the gradient of a quantum circuit, and it's actually analytic. At least when you have a perfect accurate simulator, it's analytic. The standard alternative to the parameter shift rule is this finite difference approximation. So this is a numeric approximation to the derivative, whereas the parameter shift rule is exact. Of course, in practice, we have noisy devices, so they're both realistically an approximation, but at least we know this one should be hitting the mark a bit better. So these are the two main ones, parameter shift and numerical finite difference. There's a couple of intermediate ones. So there's this classical backpropagation approach. So what this does is it lets you, if you have a simulator, so if you're not on actual quantum hardware, but you're simulating on a standard computer, then all we're really doing is a sequence of, I guess, linear algebra calculations. So then that leads itself to, we can just backpropagate through using the built-in functionality from, say, PyTorch or TensorFlow, for example. So this reversible one, it's a bit of a mix between classical backpropagation and parameter shift. I won't go too much into the details, but the idea here is that there's basically like a couple of approaches, and they all have different strengths in different areas. So Parameter shift, of course, is very hardware focused because you can't do backpropagation on a quantum hardware device. But this classical backpropagation can be more suited to, of course, simulators if you've got a lot of parameters. So as well as in PennyLane saying we have a QNode, so we can input some non-quantum data, we can do some processing, and we can get some non-quantum data out. So this is a QNode. You can also think, let's go one step beyond that and start to construct hybrid models. So as well as just getting a QNode, let's stick in, this could be something simple here. This is a cosine and a square root, but you could even have something more complex, like a neural network, for example. So this is linking back to this transfer learning that I mentioned, where we had a classical neural network coming in and then a quantum circuit. So that, yeah, this really lets us be very free in constructing these classical quantum hybrid models. And really the philosophy here is that you can split out the demand. You can say, let the classical nodes of this graph, let them do the things that they're strong at, and let the quantum parts do the things that they can focus at, that they're strong at as well. And of course, this is then fully end-to-end differentiable in PennyLane. So PennyLane is also framework and hardware agnostic. What do we mean by that? Well, there's kind of two sides of the coin. So on the one side, there's working with the machine learning packages. So there's TensorFlow and PyTorch. There's also NumPy, which actually can be done through AutoGrad, for example. So that's another package, AutoGrad, that kind of supports a NumPy style of backpropagation. So then on this side, PennyLane can interface with whichever one you choose. If you've got code in PyTorch, it can naturally work with PennyLane. Same with TensorFlow. But then there's the other side of say lower down, how do we simulate these quantum circuits? So, or how do we run it on hardware? So we're not stuck to using a Xanadu simulator. You do have an option of using Strawberry Fields, which is our simulator and hardware access point for our photonic hardware. So you can run on a photonic hardware and simulator, but you can also say, I want to run my device on, I want to run my simulation on Qiskit. You can also run on Qiskit hardware, for example. So you're very free to say, simulation 1, PyTorch, Qiskit. Simulation 2, TensorFlow, Strawberry Fields. We really do see it as this sort of jigsaw puzzle. And another thing that I want to emphasize is, I mentioned that you can choose your device. You can choose software, you can choose both a simulator-based device, but also quantum hardware. But the key is that you can combine as well. So you can have a hybrid graph again. And here we have a node that's a qubit-based device. But further on down, we actually have a photonic-based device. And I haven't dug too much deep into this, but the idea is that the photonic approach can have a slightly different set of gates, really. It's like a slightly different model, and that yields a different set of gates and a different way to describe the quantum system. But you can wrap both of the qubit and the photonic approaches up into this QNode perspective. And then, yeah, they're just nodes in this bigger computational graph. So you can be evaluating one thing on a qubit device, then send it through, and then the photonic device can be depending on that, for example. And that can be used as a sort of very flexible model of hybrid machine learning, quantum machine learning. So another cool thing that we've focused on is, okay, there's TensorFlow, there's PyTorch, but they often have a slightly higher level functionality where you can much more easily design neural networks, for example. So the TensorFlow equivalent is Keras. And there it's easy to, say, have a couple of feed-forward dense layers. And it's kind of nicely set up to train, to optimize. So we, of course, want PennyLane to be able to integrate with the higher level as well. So this is something we've added a bit more recently, actually. You can naturally convert your quantum system into a Keras layer. So instead of having a QNode, it converts into a standard layer that can be treated just like anything else, any other layer in Keras. The same with PyTorch. So you can have a torch NN layer here. So here's some code. Really, it's pretty simple if you're familiar with Keras. So we're just defining this sequential model here. And this Q layer, this is actually behind the scenes, it's a quantum circuit. It can have a bit of complexity there. But when it's wrapped up into this, this nice QNN.Keras layer object, you just treat it like a standard Keras layer. Then it's very simple to do things like fitting the model, for example. So if you're interested, if I've whet your appetite for more information about Xanadu, please check out our tutorials at PennyLane. We try and make them very accessible. There's sort of different levels. So if you want to go beginner, you want to go more intermediate, there should be something for you. So please check that out. I also wanted to, I think I have a bit of time, so I wanted to actually show you a quick demo. I hope this is still visible. Otherwise, I'll have to record my video again. So here the objective is that what we want to do is very simple problem. We've got this moons data set from scikit-learn. So let's just load it up. Okay, very simple thing. It's got one class that's kind of one moon, and then a moon that's flipped in the other direction as another class. We can't fit very easily like a linear classifier to separate the two. So it's an interesting, very prototypical machine learning problem. So this is just something quickly that I'm going to show you on how you can train a hybrid quantum model to classify. So the first step is let's set up our QNode. So we import PennyLane. We define how many qubits we want. Here we've got 2. We pick our qubit device. So this is just the standard device that we pick, default qubit. And now this part here is loading in our circuit. So we're actually, to keep it simple here, we're just using some templates. So often if you don't want to go too much into the details of how this quantum circuit looks, how to pick which gate and where to put it, we've got some templates for you. So this one lets you embed non-quantum data into the circuit. These layers are our sort of processing part, and then we have the measurement come out. So this is loading up our QNode. Now this step is, I just talked about it, is converting to this Keras layer. So we have, here we're saying let's have 3. The nomenclature can be a bit confusing, but here we're having 3 quantum layers. So 3 repetitions of our quantum circuit. And yeah, this is what we're doing here. We're defining this Keras layer. And this is a visualization of our circuit, just to make it clear. So you can see the 3, this is one layer. Sorry, this is one layer. These 2 bits. This is another layer. And then this is the final layer. So there's 3 layers on the quantum side. Together, we call this the QNode, and we're going to convert this composite into a Keras layer. So that's what we do here with this QNN.Keras layer. So now we've got that. It's just a case of making our model in Keras. So we're keeping it super simple. 2 neurons for our a standard neural network layer. So that will be the input to our quantum layer, and then we have another 2 neurons that come out, and we apply a softmax. So keeping it super simple, we define our optimizer. Again, stochastic gradient descent, fairly simple. Usual stuff in Keras, so we're picking a loss function, and then it's a case of fitting. So, okay, this is all, I guess, fairly familiar to a lot of you, but the cool thing is that behind the scenes, there is a quantum circuit being trained right now. You don't have to worry about it. We've built it in through many layers of abstraction, but we've just trained a quantum circuit. Well, actually, we've trained one epoch. So actually, I'm going to load a model here and just do a quick visualization. So here we go. And I did look at the model before. It's not the most exciting result. It looks to me like we've fit a linear classifier, but really, it's probably to be expected. We had 2 neurons and then a fairly simple quantum circuit, and then another two neurons. So if we manage to, get a bit more width in, so this is a hybrid, of course. So if we have a bit more width on the classical side, And if we have a bit more width and depth on the quantum circuit, maybe it would be a bit more exciting. But really, this was just to show you how easy it is to get started with designing and training a quantum circuit and a quantum hybrid model. So that's all I had to say. I hope you enjoyed the talk. Thanks for listening. I should be available now for a question and answer session. We're also hiring, so if you enjoyed the talk a lot, feel free to check out. So this is our main website, and there's a link to our hiring page there. Thank you very much for listening.